Hi everyone, welcome to my video. And today my topic is Hilbert space. Because of the time limitation, I will not go through all of the theorems and conclusions of the presentation, but I will still go through some significant ones. Okay, let's start with Hilbert space. So the definition of Hilbert space is Hilbert space is a vector space H with an inner product space, inner product Fg. So notice there's an inner product. So it is a inner product space such that the norm F defined by the square root of the inner product of the cell themselves turns H into a complete metric space. So complete metric space shouldn't be a very difficult term to understand. So I will not go through it very deeply. So now we'll go to another special kind of Hilbert space. It's called L2 space. So L2 space is a set of complex valued functions on the real number line with the integral on the real number line of the square of the norm of f converges. It's literally a set of functions that satisfies this property. And inner product is defined as the integral on the real number line of the first function times the conjugate of second function. So this definition of Hilbert space and L2 space. And we are able to prove that L2 space is literally a kind of Hilbert space. We will not go through here because of the time limitation. So next, we want to provide a kind of orthogonal sequence of the L2 from minus pi to pi. So first, what means L2 from minus pi to pi? This space is literally similar to L2 space. So the difference is that it is not on the real number line. It's from minus pi to pi. And same thing happened here. So we know what is L2 from minus pi to pi now. So we want to prove this space, this sequence is an orthogonal sequence in this space. So suppose Fk is a term of the sequence. Then we have the inner product of two spaces equal to this one. So remember, this is minus because our inner product space in L2 is the integral of the first function times the conjugate of the second function. So it is minus here. So we change this thing to the triangular form. We have the next one. And now we have, if k is not equals to m, then this is a x times a integer. Then we have from minus pi to pi is several periods of the triangular function. So this one equals to 0. The integral equals to 0. So if k is not equals to m, then it equals to 0. If k equals to m, we have the first one is 1 and the second one is 0. Then the integral is 2 pi and times 1 over 2 pi, then it's 1. So when k equals m, it is 1. So we have fk and fm are orthogonal if k not equals to m. If k and the norm of fk is 1. So this sequence is orthonormal. So next, we'll define the Fourier series. The Fourier series on the interval minus pi to pi is defined as below. This one, fx. And the coefficients are defined as this. So next, we'll go through the Bessel's inequality. Bessel's inequality is defined in an inner product space. We have if fk is an orthonormal sequence. We define what's also orthonormal sequence in the last proof. And for every function in this space, we have the following conclusion. This one. The series of these inner products is smaller or equal than norm of f, the square of norm of f. So we have a proof here. Suppose Sn is a partial series of the left one. Then we have, for the linearity, we have the inner product space of f minus Sn times Fk is equal to this. And we change Sn into this one. Next, we have, since this is a scalar, we put it out. Then we have this. Next, for the linearity, we have this one. We put this scalar into this inner product space. Into this inner product, we have this. And since Fk is also normal, this inner product equals to 0 if J is not equal to K, and their norm is 1. So we have following. And since f minus Sn times Fk equals to this, and this one equals to f times Fk, then this one is 0. So we have f minus Sn and Fk are also orthogonal. Then since Sn is the linear combination of Fk's, so f minus Sn and Sn are also orthogonal. So next we have this one, since f minus Sn and f are orthogonal. Since we have the norm of Sn is smaller than the norm of f, and since the norm of Sn equals to this, we have the conclusion here. So next we'll talk about Parseval's theorem and Bessel problem. So Parseval's theorem is a special case of the Bessel's inequality. It states that if Fk is complete, we should know what means complete. It means the Cauchy sequence converges. Then the inequality of the above theorem become equality. So notice that if there is a Fk complete sequence in the inner product space, then this space is literally a Hilbert space. So next, for the Bessel problem, we want to show that the series of all inverse of the perfect squares equals converges to pi square over 6. We can use Parseval's theorem to prove this, but we will not go through because of the time limitation. So now we have Bessel's inequality and Parseval's theorem. We also have the definition of Hilbert space, L2 space, and Fourier series. Now we want to define the one we want to prove for the L2 convergence of Fourier series. So the definition of L2 convergence of Fourier series is that for a sequence Fn and a f function f in the space L to D, D refers to a subset of the real number set. Then we say that the sequence Fn converges in norm if it satisfies the following: Fn minus f norm equals to 0. So this 2 means that the square root of each of the square of the sum of the square of each term in this function. So still, though we have Bessel's inequality and the Parseval theorem adheres, we still need many steps to prove this. It's significantly difficult in this presentation to provide the complete proof. Literally, it takes me about more than 1 week to figure out each step of this proof. So it should be the most difficult part in this project. Yes, so we'll stop here. And that is all for my presentation. Thank you for your watching. And that's it. Wish you have a nice day. Bye-bye.